in Newtonian fluid has the following velocity field: V is equal to x square y I bar plus 2xy square z 2xy square z j bar plus yz cube k bar. Here, so the rate of shear deformation at the point x is equal to minus 2, y is equal to minus 1, z is equal to 2 for the given flow is. Here we know that the rate of shear deformation is given by, or the rate of shear strain is equal to half dou v by dou y plus dou u by dou x. So here in the given field, that is v is equal to x square y plus 2x square yz plus yz cube k bar. Here in this, the first term, that is in the I bar, it gives the velocity in the x direction, that is u is equal to x square y, that is u. And here in the second term, 2xy square z is nothing but the velocity in the y direction, that is v is equal to 2xy square z. So that here the shear strain rate is equal to half dou v by dou x is, sorry, here dou v by, sorry, it is dou v by dou x and dou u by dou y, sorry. So that dou v by dou x is 2y square z and dou u by dou y is just x square. Now substitute these two all the values, that is at the point x is equal to minus 2, y is equal to minus 1 and z is equal to half into 2 into 1 into 2 plus 2 square, so which is equal to 4. So here the shear strain rate is equal to 4. Exhaust gases flowing through the tubular heat exchanger at the rate of 20 kg per minute are cooled from 450 degrees centigrade to 150 degrees centigrade by water initially at 20 degrees centigrade. The specific heat of gases may be taken as 1.13 kJ per kg Kelvin and overall heat transfer coefficient may be taken as 140 watt per meter square. The surface area needed if the water flow is 25 kg per minute for parallel flow is. So here we'll have to find out the how much surface area needed to cool the exhaust gases from 450 degrees centigrade to 150 degrees centigrade in a parallel flow heat exchanger by using water initially at 20 degrees centigrade, and the water flow rate is 25 kg per minute and the exhaust gas flow rate is 20 kg per minute. And here specific rates are also given. A specific heat of the gases given as 1.13 kJ per kg Kelvin, and specific heat of the water we know that is 4.18 kJ per kg Kelvin. Now we will have to find out the surface area needed, that is that can be calculated by using the formula, that is heat transfer is equal to UA into delta T M. So here delta Tm represents logarithmic mean temperature difference, and A is the surface area needed, and U is the overall heat transfer coefficient, and Q is the heat transfer. That means either heat gained by the cooling water or heat lost by the exhaust gases. So here heat lost by the exhaust gases is equal to heat gained by the cooling water, that is mCp delta T of gases is equal to mCp delta T of water, cooling water. So here, and the logarithmic mean temperature difference is nothing but delta T1 by minus delta T2 by ln of delta T1 delta T2. Here delta T1 is the initial temperature difference of cooling water and exhaust gases, and delta T2 is the temperature difference at the exit. That is, in case of parallel flow heat exchanger, let us say exhaust gas enters at 450 degrees centigrade and leaves at 150 degrees centigrade. So in the parallel flow, both the fluids flow in the same direction, so that here water enters at the 20 degrees centigrade, and here we will have to find out the exhaust temperature. Let us say this is TW naught. So here this difference is called delta T1, that is 430. Delta T1 is equal to 430 degrees centigrade, and here delta T2 we'll have to find out first TW naught. So TW naught can be calculated by using this relation, that is mCp delta T of gases is equal to mCp delta T of water, that is heat gained by the water is equal to heat lost by the gases. By using this relation we can calculate the exhaust temperature. So that is given by 84.8 degrees centigrade. So now we have here 84.8. So that delta T2 is equal 65.2 degrees centigrade. Now by using delta T2 and delta T1 we can calculate the logarithmic mean temperature difference, that is equal to 193.4 degrees centigrade. So now we have all the values, that is heat transfer delta Tm, that is logarithmic mean temperature difference, and overall heat transfer coefficient, that is given by 140 watt per meter square. So now we can calculate the surface area needed. So that is equal to Q by U into delta Tm, and here Q is MCP delta T. So let us say 1.13 into, and here the mass flow rate is 20 kg per minute, that is 20 by 60 into delta T is 450 minus 150 by U is 140, and here delta Tm is 193.4. So by using this equation we can get the surface area, that is a water jet of diameter 90 mm strikes a series of plates arranged on the periphery of a Pelton wheel. The efficiency is maximum when the wheel rotation with a velocity 20 meter per second. What is the work done? Here I will have to find out the work done. That is, work done is given by, for a moving velocity, for a moving blade, rho av into v minus u into u. So here u is the velocity of wheel and v is the velocity of jet, and here rho is the density of water and a is the area of the jet. Here area of the jet striking is equal to pi by 4 d square, where d is the diameter of the jet, that is given 90 mm. So pi by 4 into 90 square, which is equal to nearby 0.64 meter square. Now we will have to find out the velocity of jet, and the velocity of the wheel already given, that 20 meter per second when the efficiency is maximum. So here for the maximum efficiency, velocity of jet is equal to 2 times the velocity of wheel. So that here 2 into 20, which is equal to 40 meter per second. Now the work done by the wheel is equal to 1000 into the area of jet is 0.64, and here it is 40 into 40 minus 20 into 20, which is equal to 10.24 megawatts. So the right answer is 10.24 megawatts.